Great. Okay. So we left off last time having completed our tutelage on the energy levels of the Lyman series, the line profiles, the cross-section. These transitions, I defined for you optical depth and column density, perhaps reviewed for some of you the curve of growth concept, and now have stepped into some of the descriptions related to spectroscopy. My interests are from the observational side, and the data we collect, of course, goes through a spectrometer when it comes to absorption lines. I impressed upon you that, of course, to observe Lyman-alpha, we need photons in the rest frame at 1200 angstroms. And quasars are very convenient in that respect, in that they're quite hard spectra compared to most sources. I'm showing the Lyman-alpha forest region, if you will, of a composite quasar spectrum generated from HST data, just to impress upon you again that, yes, quasars are roughly continuum sources, almost flat continuum sources in the far ultraviolet. Although there are bumps and wiggles here that are real. This here's Lyman beta, and there's additional Lyman series emission in the quasar spectra, and additionally a whole bunch of iron complexes and a bunch of other things I think we don't even know about still today. The continua are quite complex. And in order to do our analysis, we need to account for these bumps and wiggles because we're not interested in them. We're interested in the absorption features that lie upon them. And the spectrum you get, and I'll go through slides to generate the spectrum in a few minutes, may look something like this. And the blue is the original quasar continuum, and the black would be the absorbed continuum. And the game of continuum normalization, and it is a bit of a game, as I'll show you in a moment, is to take a guess at that blue line, given the black line. Okay, so that's a difficult problem, to say the least. And as I was starting to say last time, a lot of the approach traditionally has been by hand, truly. And so hopefully I won't spoil your breakfast, but I'm going into the underbelly of absorption line research. This is kind of like showing you the flat fields of deep narrowband imaging or the correlation matrices in an IFU spectrometer. But I think for school, if you can handle it, it's worth your seeing at least once. So let me just show you first a spectrum unnormalized, similar to what I just presented to you. This is a quasar at around a redshift of 3. There's the Lyman-alpha emission. Carbon-4 emission, and you can see a number of absorption features outside redward of the Lyman-alpha. Those are metal line absorption features. And then down here is our, again, Lyman-alpha forest and absorption features from hydrogen, including a very strong damp Lyman-alpha system. So again, the game here is to estimate a continuum for this spectrum. And in the notebook that you can have is code, oops, that crashes. Oh, there's the same spectrum, fine. All right, so a code has been written to make a first guess at the estimation of the continuum. So again, the data are being plotted down here in the lower panel. And every maybe 20 or so angstroms is a red dot. That's an estimate of the continuum level based on the actual data. It's a guess. You'll see in cases outside of the redward of the Lyman-alpha line, it's not such a bad guess, at least when you're away from absorption features. And then by hand, I really do mean by hand here. You are analyzing the one may look at the red curve. That's our estimate of the continuum, and decide whether or not that's a good representation of the unabsorbed flux. To guide the eye up top here are residuals between that model and fluctuations of the data, but I mean doing it by eye. And this has been the state of the art, if you want to call it that, for decades. Not so hard outside the line of forest, and indeed, I myself wouldn't take this approach. You can use the data, the flux itself, to model and make estimates of the continuum, essentially fit a high-order polynomial to the flux in these cases where the data is not heavily absorbed, masking out the regions that have obvious strong absorption features. But as I hopefully impressed upon you in the figures, the composite quasar spectrum and the absorbed composite quasar spectrum. Once you get into Lyman-alpha forest, I'd say all bets are off, particularly in the presence of a strong absorber like a damp Lyman-alpha system. And so here we have, the continuum. Where do you want to place it? You could see this is a somewhat higher resolution spectrum than Sloan, the Sloan data I showed you a moment ago, but clearly we're overabsorbed. But even here, the intergalactic medium has sufficiently sufficient amount of absorption within it. It's possible that none of these flux points. I'm struggling here a little bit. Let's just go out here. There. It's possible that none of the flux here is entirely unabsorbed. That is to say, the true continuum may lie above all the flux data points. All right. And so if our goal here is to be, if we had hopes of being sensitive at that level, very small optical depths, you can see that this continuum normalization becomes our number one uncertainty, dominant source of statistical uncertainty. I can improve the signal noise of the spectrum, and I really won't necessarily improve my estimation of that continuum normalization. So clearly, this limits some of the analysis we can do, at least if we feel we have to do this by hand. That's not necessarily the case, but it has been kind of the main technique for years and years. I think that's probably enough of that. More modern approaches, particularly when you get to large data sets that are accessible from the Sloan Digital Sky Survey, for example, it would be difficult to rely on the hand unless you had an army of graduate students or undergraduate students. So another approach is to take advantage of the fact that quasars do resemble each other by and large, despite the differences on a case-by-case basis. And now Suzuki, about a decade ago, pioneered a nice technique taking advantage of principal component analysis, where we decompose a quasar spectrum we use first a set of quasar spectra, a training set, if you will, to generate a set of eigenvectors. That's what these Kasai, or how do you say that letter, represent down here. A set of eigenvectors that hopefully describe the variations within the quasar continuum of high-redshift quasars. And then we can use that eigenvectors to both model the emission outside of the Lyman-alpha forest, where there's not so much absorption, and make even predictions, extrapolate to some extent into the regions where they're heavily absorbed by the intergalactic medium. So Q is any quasar spectrum, U is just the mean quasar spectrum, which I've been showing examples of, and then these Kasais are the eigenvectors, and the approach is not to use every eigenvector that you would generate to describe, say, a training set of 50 quasars, but the first n, or n maybe 5, maybe 7, something of that order, which hopefully contain most of the variations within the emission. And they do. These are somewhat complicated graphs from his paper, but on the left panels here, maybe just focus on those. These are the eigenvectors describing the emission from the quasar spectra. They're not physical. This is a mathematical formalism. You can adjust PCA analyses to be a bit more physical than say he did, but nevertheless, they're usually not physical eigenvectors, but just a mathematical description of the data. Here you see the Lyman-alpha emission, carbon-4 emission, Lyman-beta emission. That's the first principal component. And then these are all adjustments to the continua that are mathematically preferred to describe the variations that you see from quasar to quasar. Right? And so, and then he shows the first 10 eigenvectors. But most of the variance, this is showing the variance, or the fluctuations in the eigenvalues that you would use to fit the quasars. By, say, the fifth eigenvector, the variations in those constants, those eigenvalues have gone down, and you've more or less captured most of the variance, even the first few components, I guess 3. Here's a modern example from Isabelle Paris. And so that's her prediction For the continuum outside the Lyman-alpha forest is where the analysis is done, the extrapolation to some extent is now done within the forest. And compared to what you saw me suffer with by eye, that's obviously not such a bad effort. The danger here, however, still is that I will model this in a moment, it's very unlikely, despite the fact that red line's touching like all the peaks of the flux, it's very unlikely that's still the case. The intergalactic opacity is high enough that that's highly improbable. And so despite being a nice model by eye, it's still probably systematically biased and too low in this example. For some of the cosmological analyses, for many of the cosmological analyses actually, we've more or less given up on getting the normalization correct of the continuum. It's just too difficult to problem, and I've instead relied on analyzing the fluctuations about the mean. And so something called mean flux regulation is apply this PCA as you see above, but then within the Lyman-alpha forest, just say we're going to let the normalization settle down to the value that that gives us the mean opacity that we measure from other data sets. I'll say that again. Within the Lyman-alpha forest, just adjust the normalization to provide me with the mean opacity of the intergalactic medium that we recover from other analyses, and I'll be describing those other analyses later today. So within the Lyman-alpha forest, as I said, again, perform a PCA analysis and you get some guess in black of what the normalization could be, but then reset that normalization such that you get the mean opacity that's observed or has been derived from other spectra previously. And so now this dashed line is our estimate of the normalization, pseudo-normalization, and all the analyses are now done on fluctuations off that normalization, and that encodes a lot of the cosmological signal that we are interested in. I'll return to those types of efforts on Friday. All right, any questions on the underbelly? Hopefully I haven't turned you off to the field entirely by showing you some of the struggles we have to go through. Fine. Since I suspect many of you have yet to even touch a quasar spectrum, I thought it'd be useful to walk through. I've showed you the Lyman-alpha forest quite a few times already. Oops, not that one. That one. But haven't even really described how it's built up. This is the resolution figure from yesterday, just to remind you some of the implications of resolution. But let me build up a Lyman-alpha forest from scratch, if you will, so that we're all on the same page on how you get this series of thicket of absorption features. It's somewhat obvious, but at the same time also a bit subtle. Okay, so the easiest thing is think of yourself in the quasar rest frame. That's what's being plotted here, rest frame wavelengths. And here's our quasar, say, at a redshift of 3. And appreciate, I think you do, that to the left here, you're talking about higher and higher energy photons. Right, fine. Emitted by the quasar. As you know, as those photons leave the quasar and travel towards our telescope, they redshift due to the expansion of the universe. Fine. Now, consider some hydrogen gas right at the source, so enveloping this quasar. You now know that one will see absorption from Lyman-alpha, imprinted now on the continuum, and Lyman beta. And I'm not going to plot it, but there would be Lyman gamma, delta, right, the full series of Lyman series lines heading down. Okay? And so, sure, this gas absorbs the photons at 1025 angstroms in the rest frame of the quasar, at 1215 for Lyman-alpha. Makes perfect sense. And then you see in our observed wavelengths, okay, once those photons have redshifted all the way to Earth, you can get a 3+1 redshift in the observed wavelengths. But now think about a gas at a redshift of 2.8. That imposes absorption at Lyman-alpha and Lyman beta at these wavelengths. And the way you should view it is that it's going to absorb photons that are higher energy than Lyman-alpha in the rest frame of the quasar. They travel, right, from the quasar to the gas and redshift, and these 1155 angstrom photons eventually become Lyman-alpha photons, having redshifted, and so, hence they are able to interact with the gas or be absorbed by the gas at a redshift of 2.8. And so that's why you visualize as you go to the left in a Lyman-alpha force spectrum heading towards lower redshift, despite the fact these are higher energy photons. It's a little bit confusing. But it's the notion that you have to start off at a higher energy redshift into resonance and then be absorbed by the gas at a lower redshift. Similarly, going down to redshift 2.5, now you have photons that have to start at 1060 angstroms and redshift all the way through intergalactic space, become in resonance at 2.5 and be absorbed by the gas. To make matters a bit worse or to complicate the story, that continues on and on. As you, right, in terms of Lyman-alpha, that continues on and on as you go down to higher and higher energies or lower and lower rest wavelengths. So that gas at 2.2 can and may well absorb at exactly the same wavelengths as this gas, this Lyman beta feature that is associated with the gas at redshift 2.8. So we have additional opacity at for these photons. The way you should view it is that these photons redshift from here to here, become resonant at Lyman beta at 2.8, and then resonant in Lyman-alpha at 2.2, and you get absorption on top, dual opacities at 970 angstroms in the rest frame, or whatever, 3,900 angstroms in the observer frame. Putting it all together, allowing for gas all along the sight line, you get complexity of the Lyman-alpha force that you see in the spectrum. Okay. So you should be now viewing, if you haven't been, the Lyman-alpha force as a declining redshift in terms of Lyman-alpha, but then considerable complexity once you get blueward of the Lyman beta emission line, because you have all the additional Lyman series opacity in play. Any questions on that? All right. Don't think of any more there. Goodbye. Come back later. So I had just a few more notes on measuring equivalent width. Maybe I'll go through those very quickly. From an absorption feature, there are basically two approaches to measuring this equivalent width in the data. To sum over the pixels, we'll call that simply a boxcar analysis. So that I'm just summing over every pixel in the absorption feature, 1 minus the normalized flux times the width of the pixel. That gives you the observed equivalent width. You can fit a Gauss into the feature. You could even fit a void profile to the feature. I put some notes in the notebook that you can look at. You should appreciate that while that's would be done in your observed spectrum, the physical quantities are associated with the rest equivalent width, and so it's trivial, but you have to divide by 1 plus z to convert from that observed equivalent width to a rest equivalent width. For the observers in the crowd, if you're writing proposals, say for HST next week or week after, and need to consider the sensitivity of your observations, I've put in some let's go through this, I guess. You need to ask for the proposal, what is the limiting equivalent width? What's your sensitivity to absorption? So you can ask, what's the limiting equivalent width if you want to measure some spectral feature? The uncertainty associated equivalent width over some absorption profile is given by this equation. The square root of the number of pixels that you have to integrate across. That may be one resolution element. That may be many more pixels if you have a very broad feature. Times the dispersion and divided by the Signal noise. The uncertainty in the normalized flux is actually just the inverse of the Signal noise. And that's just a 1 sigma uncertainty. If you want to have a n sigma detection in the data, then you need to consider n sigma limiting equivalent width, say 3. And I put in the notes just a simple calculation of that for, say, a spectrum with a resolution of 2,000, signal noise 10 per pixel. The limiting equivalent width is an angstrom. Maybe that's a number to walk away with. So thinking of the thousands and thousands and thousands, and soon to be maybe a million, R of 2,000 spectra that we're getting from these major surveys, even at the highest quality, that is quite high quality for those data, you're only sensitive to an angstrom in equivalent width. And just remember back to the curve of growth yesterday, an angstrom equivalent width puts us on that saturated portion of the curve of growth. So most of those data, you're only sensitive to saturated features or stronger, not at all sensitive to the weak portion of the curve of growth, which is to say you don't have very good sensitivity in such data to the column densities. And you saw that visually when we plotted up the line profiles, but you can also estimate that from just the equivalent widths. And then I think I will just skip over that. There's also line profile fitting techniques I put in the notes too. Modern packages for doing such analyses, and in the notebook an example just for a very simple line, but I think I'll skip over that. Okay, that was kind of a quick review of some of the issues related to spectroscopy that affect our absorption analysis. Now let's go into characterizing the Lyman-alpha force itself. And this lecture will, or this set of notes will go across 2 lectures now in the end of the day. I have a number of goals in mind. It's to provide this concept that I'll call f of n, the distribution function of column density, is to provide an empirical formalism for characterizing Lyman-alpha force, the undulations that we've been seeing in these spectra, discuss the modern observational constraints on that, the implications and applications that you get once you've made that analysis. And along the way, I guess you should keep in mind that really fundamentally any precise estimate that we can make of the intergalactic medium in the data does offer, or at least should offer, a powerful constraint on our modern cosmology. And the point being, in the CDM cosmology, we do have this very clear and clean prediction of the intergalactic medium. It's an undulating density field, as I've mentioned once before. And on quasi-linear scales, so if you stay away from galaxies in particular, the baryon should be tracing the dark matter. So insofar as we can predict how the dark matter is distributed in the universe, and we now feel we can do that quite well, then the intergalactic medium gives you a clean measure of that density field, and you can do modern cosmology with it. So any precise measurement really can and should be able to place a tight constraint on our cosmology. Just a reminder, most of the discussion here is on optically thin gas. There'll be future lectures on optically thick gas. All right. So, let's start off by this. Someone asked if you could have that very nice 1422 spectrum. So sure, why not? Let's explore the Lyman-alpha forest a bit in the data. You've seen some of this, but here we are again. That's real data. That's not simulated absorption lines. Okay, the signal here is exquisite. But what I'm trying to impress upon you here, and I think maybe you've already captured this, is that it does make sense to go forth and describe and characterize, at least empirically, the Lyman-alpha forest as a series of individual absorption lines. Hopefully, you've now come to that conclusion yourself. It's exquisite. So that is the approach here. Our attempt will be to characterize the IGM as a series of absorption features, and we'll characterize the distribution functions of those. Let me also impress upon you evolution in this Lyman-alpha forest. Oop, not that one. Sorry. There we go. Crash my computer. So I'm going to slide through a series of observed data of the IGM in pretty small snippets of redshift space, around 0.3, and give you, again, a further visual impression of what we're attempting to characterize here with this f of n description. So redshift of 2, redshift of 2.5. Can I blink back? Yeah. They look about the same, perhaps a bit more opacity. On redshift 3, it's clear now that the average opacity is rising. That is to say that the number of absorption, the amount of absorption, the number of these absorption features is quickly increasing. Redshift 3.8, the forest thickens even further. It's getting to be a bit of a scary place. Redshift 4.2, 4.6, 5. Now, I assure you, there's not a single pixel in any spectrum that anyone's ever taken, okay, of the redshift 5 source that isn't absorbed by the intergalactic medium to some extent. All right, so now the opacity is such that tau is at least several tenths at every single wavelength throughout the spectrum. And then redshift 6. The IGM has wiped out any signature of the source at these wavelengths. Okay. Back to 2. And let's go the other way. That's a redshift 1. This is now the actual ultraviolet. This is the thinning of the Lyman-alpha forest. As we head towards the modern universe, there's much less opacity within the data. And here's today. By our own time, the forest is more or less gone. Okay, very few observable features. So we wish to characterize that in addition to we need to characterize that redshift evolution in addition to the absorption-like nature of the forest. So that's the concept, is to model the data as a series of absorption features. It takes a heroic effort. Let's give you a sense of that heroic effort. This is the PhD of David Kirkman, who had access to some of the early Keck data. And probably from the back of the room, you can't even tell, he has fitted, with the void profile analysis, all the absorption features within these data. And the marks up here are the column densities and these Doppler parameters for each of the features that he's got in the data, just to convince you that there is a model there. He has painstakingly go through and analyze with this void profile formalism each one of these features, occasionally finding metal features or occasionally identifying absorption unrelated to hydrogen, kind of throwing that out, and doing it on again and again, angstrom after angstrom throughout the data. Tae-Sun Kim also did it for her thesis. There is a model there, I think. And each of these hash marks now is an additional absorption feature, this showing the residuals between the model and the data. And you can, I think, agree she's done a heroic effort to characterize the data. So very expensive process, to say the least, in terms of human terms. But at the end of the day, they generated a distribution of column densities and b-values describing the data as a function of redshift. The advantage of this technique is that it does capture this formalism, is that it does capture the stochastic nature of the forest. It does capture the absorption line appearance of the data. It does enable, as you'll see, calculations of other valuable measures. And it's primarily an empirical, well, it's not just primarily, it really is an empirical description. So there's no modeling here other than the effort that's required to put profile fits onto the data. So no a priori assumptions about what the origin of the data of the IGM is, what the cosmology is, things like that. Of course, that's as much a con as it is a pro, because that means what's been done here is not a physical model; it's a purely empirical description. There's some other negatives to this approach, which is why we're using it less and less these days. It's difficult to derive these quantities to do that type of profile fitting, for example, on simulated data, if not impossible. Very expensive to do. The human interaction, so the fact that these graduate students went through and performed this line profile fitting, they are humans, and depending on how sleepy or annoyed or bored they were with the process, assuredly came up with different results. So there's a human interaction that makes it somewhat non-producible. And the last one's a bit. Okay, so let me now define f of n. It's the number of absorption features, some number of lines in the intervals of these column density intervals, interval of Doppler parameter interval of redshift. And you should be thinking of it very much like one would for a luminosity function. For a luminosity function, you think of some volume, and within that volume, you've got a whole bunch of Lyman-alpha emitters, for example, with a range of luminosities, and we count up the number of Lyman-alpha emitters as a function of some luminosity interval in that volume, normalized by the volume, and you wind up with a luminosity function, say phi of L, right, with some distribution, often a gamma function. The concept's similar for absorption, but now you should be visualizing, you've got a source, and you've got absorption features along the path, and we are counting up those lines and say as a function of column density, determining a distribution function, maybe a power law, maybe also a gamma function, that describes how many of those absorption features occur per unit redshift and per column density interval. Okay, so very analogous to the techniques that are used for characterizing the galaxy distributions. We are adopting the same formalism, or concept at least here, for the number density of the absorption. A standard assumption, and it's a good one, is that the distribution of the velocity widths, the Doppler parameters, may be separated from the distribution of the column densities. So we can separate in the two quantities and measure them independently. And I'll show you measurements of each. Okay, survey path. For the galaxy example again, in order to normalize this luminosity function, you have to appreciate how much volume you surveyed within your data set. The concept's similar, again, analogous for absorption, except for it's the survey path, so it's the amount of path length that you've surveyed for the absorption features. I use the notation of a delta z. I think I put in a cartoon. Not that. That. There. Okay, so again, basically what I've drawn on the board here, we have one quasar where we've characterized the absorption features along it over some redshift from the source, say redshift 3 here, down to some lower redshifts, perhaps 2.5. And then we repeat the experiment on sources that may have different starting points, different redshifts of the source, count up the lines, continue on, have multiple sight lines to build up statistics. And then we define a smaller volume, say within the data set, so that we can explore redshift evolution. And now I'm just going to perform the analysis over this small slice in the universe, say 2.7 to 2.85. Each quasar then contributes a redshift interval of about 0.15. And the total path length of the survey, given I have 4 quasars, is 4 times that, or a delta z of 0.6. All right. So f of n, the distribution functions then is just derived from that slice of the volume of the universe that we can derive from these series of sightlines. That's what I mean by survey path.
Why is the survey path so small?
In this example?
Or is it so it varies a lot?
Well, I can continue to add more and more quasars, of course, but each one is only contributing, whatever, a delta z of 0.15.
So why is every individual quasar survey path so small?
You mean from 3 to 2.5?
Yeah.
Coming back to when I built up the Lyman-alpha forest for you, I tried to impress upon you that once you went past Lyman beta feature, you've got opacity from not just Lyman-alpha, but beta and even principal error lines. You can attempt to account for that. I mean, with high quality enough data, you may be able to work out that, yeah, the opacity here is the sum of 3 in less, well, most folks don't want to make that effort, so they cut the analysis off once you get to the Lyman beta feature of the spectrum, and that just limits how much each quasar covers, yeah. It's, well, like a galaxy survey, each sightline or each image may have its own depth, and you have to account for that, of course. You will have eventually, when it comes to a survey, some sensitivity limit to the column density, some sensitivity limit to the Doppler parameters, and the survey path also takes that into account. I'm just showing now the formalism that I just showed you in the slides. Each quasar contributes a redshift interval, little delta z, and the total survey path is just the sum of all those individual quasars. There's a quantity delta x, which I will introduce later. Some of the slides here, you might see it. It's just a transformation from delta z. It's a simple transformation, unitless transformation. From delta z to delta x, delta x includes cosmology and has therefore is quite important, but I don't need it right now, so I'm just deferring it. Delta z, redshift, is pure observable, and I'm going to stick with that in the description, but heads up that delta x is coming. Okay, so again, like a galaxy survey, you can make a binned evaluation of this distribution function. It's the optimal estimator is just counting up, literally, the number of lines within the intervals of column density and across the entire redshift path of your survey, normalized by the size of that column density interval and the total redshift path of your survey, and you get estimates of that distribution function in a binned quantity. Since you're just counting lines, the uncertainty in that estimator is the Poisson uncertainty and the number of lines that you've got. I think I'll ignore the subtlety. So here are some very early results. Well, not very early, but early results from the late 80s and early 90s. On the x-axis is the column densities of the absorption lines. On the y-axis is this estimator. We're showing binned estimations of this distribution function, f of n. The numbers here get very large, or the dynamic range here is very large, just because the dynamic range here is very large. And again, you're dividing by the column density bins to describe the f of n. But just the takeaway point is that the feature, to zeroth order, the data follow what appears to be a power law. That's true. Zeroth order, that's a decent description of the distribution function. You'll see as we go along, it's a bit more complex than that. The data here started to show deviations from such a power law, but weren't really high enough quality to convince you of that. I'm going to really focus for the remainder of these notes on f of n on the left-hand side here, the lower column density regime. I'll come back to the higher ones tomorrow. Faced with those data, Tyler actually proposed that the entire intergalactic medium was one population of clouds. That gave rise to a single power law. I think that was a reasonable interpretation of his data, despite the fact it wasn't quite the right answer, or not even close to the right answer. And Petitjean argued for distinct populations, okay? Again, just based on simple line counting. Keck arrived in the early 90s, and folks did the analysis I was showing you earlier, the line fitting. And now I've really zoomed in on the lower column density end. And this is, again, binned evaluations of this frequency distribution function as a function of column density. The thing I'm emphasizing here is this turnover at the very lowest opacities, the very lowest column densities. This is characteristic of all the data. And again, if you're thinking about galaxies, you might say, well, there's a number of reasons this may occur. If you're thinking about galaxies, you might say, well, maybe they didn't have the sensitivity of the data to be capable of finding these lines. That is, you often see in analyses of luminosity functions a turnover that you don't ascribe to being real, but you ascribe to being insensitivity in the data. And indeed, we are talking about opacities here, or optical depths of a few percent. So very small, maybe that is the explanation. Well, I don't think it really is. Could be a poor estimation of the continuum, as I've already described to you. Estimating the continuum to a few percent is difficult, and that will affect such analyses. But I think it's either, we believe it's either a physical turnover in the universe, that is, the amount of gas that we're sensitive to at those optical depths becomes small in a nonlinear fashion, or just even a breakdown, maybe it's just as much, a breakdown in this methodology, that is, those little small absorption features get lost, buried, if you like, within our description of the stronger absorption features in the gas. Nevertheless, that turnover is real in the sense that it's not a function of the sensitivity of the data. It's within the analysis. So in coming to the modern times, the data is really now exquisite. There's no question about statistics, at least at these calm densities. And we've entered the regime, the painful regime, really of systematic errors. So I'm plotting up bin evaluations from two analyses of two separate data sets. And they are very good agreement for most of the dynamic range, which is nice. Zooming in, right? These are within, well, it's a log scale, so even that, well, no, that's within the uncertainties. But there are small or modest, let's call it that, differences in the regime, maybe not fully not surprising, in the regime where you enter the saturated portion of the curve of growth. So at these calm densities of 10 to 16, 10 to 17, where you have limited sensitivity in the data, we do see significant differences in the description of the forest that is statistically strong in the difference and must be associated with systematic errors. How much time? 2 minutes. All right, then I will stop there. When we pick it up next, I've shown you just bin evaluations now. We'll move on to modeling the data and then applying the description to make predictions of the Lyman-alpha forest. Any questions on where we've gotten to so far? Yes, sir.
That was redshift 2.4. Is there an evolution with redshift of the whole distribution?
There is over the full dynamic range of the universe, say redshift 0 to 5, undoubtedly. The shape of, not so much even the shape in these, on these condenses, maybe it's quite small, but there's a distinction in the way the lower opacity, the true intergalactic medium as we might call it, the way it's evolving compared to the higher calm density systems which we may associate with galaxies. Those do show a distinct evolution with redshift, or they differ in the way that they evolve with redshift. Mm-hmm. And you'll see that in the data for sure. Yeah. Any other questions? Okay, so when we pick it up again, we will model this frequency distribution, take those bin evaluations, take the data, not the bin evaluations, but the data, perform a maximum likelihood analysis to generate models, and then make some characterizations of the intergalactic medium from these distribution functions.